Alright, welcome to Calculus. We're going to look at optimization problems. I'm going to put the actual problem in the description for this video so you can find the actual problem there. It's pretty straightforward. I'm going to go ahead and read it out though to you. We're going to be wanting to optimize the rectangle that is inscribed inside of this downward facing parabola. So the parabola is 16 minus x squared, and what we want to do is we want to find the rectangle of largest area that can be inscribed in this in such a way that the vertices, the upper vertices for the rectangle, are on the parabola itself. So a few problems pop up as we start to work through this. But a couple of nice things are in existence too. Like you start working through this problem, like where do we even start with this? Well, a couple places that we can start, just to kind of get our bearings on what we're dealing with here, is that right here is going to be 16. Now, some of you may be thinking, well, how do I know that's 16 right there? Well, I know it's 16 because this is 16 minus x squared. So it's a downward facing parabola. Its y-intercept is at 16. So what else do we know? Well, we know if we were to factor that, 16 minus x squared, right? That would be 4 minus x and 4 plus x, right? Which means that our intercepts are right there at -4 and +4. Now, is this useful to us? I don't know, maybe it is, but getting some information written down can be useful. At the very least, we know that the rectangle is not 8 units wide, because that wouldn't create a rectangle for us. So there's that piece to it, right? Now, the next thing, well, how do we start to identify and understand what we're really dealing with? Let's do something real quick. Let's call this value right here x, which means that this is also x, and I'm talking about the distance from there to there, right? So that means that the length of this rectangle is 2x's, right? And then we have the height of the rectangle, which we'll call y, or the width, however you want to describe that. So width would be equal to y. So the area of this rectangle is equal to 2x times y. Now, we have the area equation. We know what we need to actually optimize. Here's our primary equation. This is what we were searching on needing to do. So what we want to do is we want to be able to find a prime, right? Problem with this is that we have an x and a y. We essentially have two independent variables inside of this. And then keep in mind, we could have also written this as L times W or 2L times W. However we define this out, okay? It's still going to work just fine. But what do we do with it now? We have two independent variables to deal with. If this was a related rate problem, that'd be fine. We'd have two rates to deal with. We don't want two rates here. We just want the one. So what do? Well, we have that thing. This is essentially y equal to 16 minus x squared, right? So look at what we got there, yeah? We actually have a way to replace y with something else that's equal to, which is pretty decent of us, right? So now that means that a is equal to 2x times 16 minus x squared. Now everything's in terms of one variable. So now let's do a little bit of algebra simplifying here just to make it easier to look at. So this becomes 32x minus 2x cubed. Okay, that's decent. Let's come back over here and we get our derivative now. So that means that we've got 32 minus 6x squared. There's our derivative. Now, what we need to do now is figure out what we do with all this. At this point, it feels like finding those zeros and finding the y-intercept is kind of pointless. We have it though, so who cares? But we have this area equation, so if we were looking to find the maximum area, we can do that if we know the value of x. But this question was asking us to find the dimensions that yield maximum area, which means that we need to find the length and we need to find the width of that rectangle. So what do we do with this then? Well, took area, we found the first derivative. Now if we take that first derivative and we set it equal to 0, what we're going to be doing is we're going to be trying to find the critical numbers at this point. And then we can use the first or second derivative test to determine whether that critical number or critical numbers are maximums or minimums of maximum dimension or minimum dimension, however we want to write that, right? So, a couple ways we can work this out. Since this is a constant and the x squared term, we can just write this as 6x squared equals 32. Okay, that's good. And then we can divide both sides by 6, so x squared is equal to 32 over 6, which means that x is equal to plus or minus the square root of 32 over 6. You can find that decimal if you want to. There's nothing wrong with doing that. It's perfectly acceptable. Don't need to, though. I'll show you why here in a second. But what we can do is we can actually say, well, this was plus or minus. We can get rid of the minus. Just mark it out entirely. Why? Well, because this is a dimension. We're not going to have a negative dimension here. So, okay, there we go. Now, first or second derivative test, what do we want to do? Well, what we want to do is we want to determine whether this is indeed going to yield us the maximum area. So in order to figure that out, what we need to do is show that this in the second derivative is concave down at that spot, or we need to use the first derivative test to show that it's increasing and then it decreases. So I already had the second derivative, or first derivative right here. A double prime would be negative 12x. Now I'm going with the second derivative test on this one for a very big reason. I'll show you. If you don't already see it, you can pause and try to work in front of me a little bit and see. This is going to do is negative 12 times the square root of 32 over 6. I have no idea what that number is. But what I do know is it's negative. If it's negative, it means that the function a is concave down. It's supposed to be a w. There we go. Concave down at x equal to the square root of 32 over 6, right? Well, if I know it's concave down at that spot, then what else do I know? Then that means I have a maximum at, and keep in mind, this isn't the maximum, this is where the maximum is at. We have maximum at x equal to the square root of 32 over 6. All right. So now what we have is the first value for, or the first piece of our dimension. Now, this isn't our dimension, this is the value for x. So what we got, okay, maximum dimensions. L is 2w, or 2x rather. So that is 2 times the square root of 32 over 6. Can we reduce that? Oh, almost definitely we could reduce that. But I'm not going to worry about reducing it, because really all I want is that value, right? And then the other piece, the w, well, that was equal to y. So what we do is we take 32 over 6 and we plug it into our function here. So that's 16 minus the square root of 32 over 6 squared. So that is 16 minus 32 over 6, and whatever that works out to be, okay? All right, so that's going to give us some value there that is somewhat smaller than 16. 32, if you wanted an approximate value here, 32 over 16, that'd be about 5 and a third. So that is, this value right here is roughly 11. Okay, what is that? 10 and 2/3. That's what we end up with there. And then there are dimensions. Here's our length, and here's our width. So W equals 10 and 2/3. If we had units on this, we'd stick our units on this, but this problem didn't have units to begin with, so I'm not going to stick units on the end of it at the end. What we could say is we'd say units and units. All right. I hope this was useful. Reach out with comments or questions if you have any. I'll also be posting, there should be a few more videos about this exact same topic. Have a good day. Take care.